Welcome to today's session. In this problem walkthrough, we'll tackle combination sum, a fascinating and versatile coding challenge. We'll explore different approaches to solve this problem effectively, diving into key concepts and trade-offs. Let's get started. In this problem, you are given a list of distinct integers called candidates and a target integer named target. Your goal is to find all unique combinations of numbers from the candidates list that add up exactly to the target. Importantly, each number in the candidates list can be used as many times as needed to reach the target. However, combinations that use the same numbers but in a different order are considered identical and should only appear once in the result. For example, a combination like 2, 2, 3 is the same as 3, 2, 2. The task is to return all these unique combinations as a list of lists, and the order in which you return these combinations does not matter. The constraints are also provided. The candidates list can have up to 30 distinct integers, and their values will range from 1 to 200, while the target itself can be any integer between 1 and 500. Let's look at the first example. Suppose we have candidates equal to 2, 3, 6, 7, and the target is 7. The output in this case is 2, 2, 3, 7. Here's why. One valid combination is 2, 2, 3, where the number 2 is used twice and the number 3 is used once, and these add up to 7. Another valid combination is 7, which directly matches the target. Notice that we do not include 3, 2, 2 as a separate combination because it is essentially the same as 2, 2, 3, the order of numbers doesn't matter. This illustrates the requirement for combinations to be unique. Now, consider the second example where candidates is 2, 3, 5, and the target is 8. The output here is 2, 2, 2, 2, 2, 3, 3, 3, 5. The first combination, 2, 2, 2, 2, uses the number 2 4 times to reach 8. The second combination, 2, 3, 3, uses the number 2 once and the number 3 twice. Finally, the third combination, 3, 5, uses the number 3 once and the number 5 once. Each of these combinations adds up to 8, and all of them are unique. Now, for a different case, if candidates is 2 and the target is 1, the output would be an empty list because it's impossible to form the target using the given candidates. To explain further, when candidates is 2 and target is 1, no combination of the number 2 can sum to 1, so the result is simply an empty list. Moving on to the constraints, the problem guarantees that the candidates list contains between 1 and 30 distinct integers, each ranging from 1 to 200. The target will always be a value between 1 and 500. Some edge cases to consider include when candidates has only one number, and that number divides the target evenly. In such cases, the output will consist of repeated uses of that number. For example, if candidates is 5 and target is 15, the result would be 5, 5, 5. On the other hand, if the target is smaller than the smallest number in candidates, or if no combination of numbers can sum to the target, the output will be an empty list. Similarly, if the target matches exactly one of the numbers in candidates, the output will contain that number as the sole combination. To begin, let's consider the brute force approach. The idea here is to generate all possible subsets of the given candidates array and check whether each subset sums up to the target value. This can be achieved using either recursion or iteration. For each number in the array, we make a decision, either include it in the current combination or skip it entirely, and then repeat this process for all other numbers. While this method is straightforward conceptually, it's not efficient. The time complexity is exponential, specifically 2 to the power of n asterisk n, where n is the size of the candidates array. This is because we're exploring all subsets and then verifying their sums. Additionally, this approach doesn't take advantage of problem constraints, such as the distinctiveness of candidates or the fact that numbers can be reused. As a result, it becomes computationally expensive for larger inputs, making it impractical for real-world use cases. Now, let's move to a more refined solution, the backtracking approach. This method leverages recursion to explore potential combinations while pruning invalid paths early. The main observation here is that numbers can be reused multiple times in a combination, and we can avoid generating duplicate combinations by enforcing an ordering rule. Specifically, we only consider candidates starting from the current index onward during our recursive exploration. The implementation involves a helper function that tracks the current combination and the remaining target. For each candidate, we decide whether to include it, decrementing the target accordingly, or skip it altogether. The recursion terminates when the target becomes 0, indicating a valid combination, or when it turns negative, which means the current path is invalid and can be pruned. This approach is more efficient than brute force since it eliminates unnecessary computations early. The time complexity is roughly 2 to the power of t asterisk k, where t is the target value and k is the average length of valid combinations, while the space complexity is proportional to the recursion depth, t. Although it's not the fastest approach for extremely large inputs, it strikes a good balance between efficiency and simplicity. An alternative strategy is to use dynamic programming with a tabulation approach. This treats the problem as a variation of the unbounded knapsack problem. Here, we maintain a DP array where each index x represents all unique combinations that sum up to x. The idea is to iteratively build the solution by updating the DP array for every candidate. For a given candidate, we update all DP x values by appending the current candidate to combinations that form x minus the candidate. This way, we systematically construct all possible sums up to the target value. The time complexity of this approach is n*t, where n is the number of candidates and t is the target. The space complexity is t, because the DP array grows with the target size. While this method is efficient and avoids recursion, it can be more challenging to implement and debug compared to backtracking. Additionally, it may consume more memory for large targets, which can become a limitation depending on the problem's constraints. The backtracking approach was ultimately chosen for its simplicity and flexibility. It directly aligns with the problem's requirements, making it intuitive to implement, debug, and understand. Backtracking is efficient because it prunes invalid branches early, avoiding unnecessary computations and reducing overall runtime compared to brute force. In terms of scalability, while dynamic programming may offer better time complexity, its higher space usage can be a drawback for large target values. Backtracking, with its recursive nature, is more memory efficient for moderate-sized inputs. A key insight in this approach is that numbers can be reused, and by enforcing an ordering rule only considering candidates from the current index onward, we naturally avoid duplicate combinations. This recursive structure elegantly handles the problem constraints, eliminating the need for external data structures. However, it's worth noting that for extremely large inputs, backtracking might still struggle due to deep recursion stacks. Despite this, within the given constraints, it offers a well-balanced solution that prioritizes clarity without sacrificing performance. In conclusion, backtracking emerges as a natural fit for solving the combination sum problem. Its recursive design efficiently explores all valid combinations while adhering to constraints like number reusability and avoiding duplicates through ordering. The ability to prune invalid paths early allows it to strike a balance between clarity and efficiency. Although dynamic programming might be more computationally efficient for very large inputs, the simplicity and memory efficiency of backtracking make it a better choice for the given constraints. Overall, this approach provides a clear, systematic way to tackle the problem, ensuring both correctness and performance. The problem we're solving is to find all unique combinations of numbers from the given candidates array that sum up to a specific target. Importantly, each number in the array can be used multiple times, and the result should not contain duplicate combinations. To solve this, we'll use a backtracking approach combined with some optimizations. First, we sort the candidates array. Sorting not only helps us handle duplicate combinations but also ensures that the results are arranged in lexicographical order, which is helpful for clarity and consistency. For example, if candidates equals 3, 1, 2, sorting it gives 1, 2, 3. Next, we define a recursive backtracking function called findCombinations, which takes parameters such as the current index, remaining target, the combination we're building, and a result list to store valid combinations. This function will systematically explore all possible combinations of numbers while adhering to the constraints of the problem. For the recursive function, we define a couple of base cases. If the target becomes 0, it means we've successfully formed a valid combination, so we add the current combination to the result list. However, if the target becomes negative, we stop the current exploration since adding any further elements will only take us further away from the target. Once the base cases are in place, the recursive exploration begins. Starting from the given index, we iterate through the candidates array. For each element we included in the current combination, reduce the target accordingly, and make a recursive call to continue building the combination. Importantly, we pass the same index in the recursive call to allow reusing the current element. After exploring that path, we backtrack by removing the last added element from the combination, which resets the state for exploring other possibilities. Finally, we move to the next candidate, ensuring that we systematically explore all distinct combinations without duplication. There are a few key insights to consider when implementing this algorithm. First, sorting the input array ensures that combinations are generated in lexicographical order, which automatically prevents duplicates like 2, 3, and 3, 2. Second, we use a pruning technique to stop recursion whenever the target becomes negative, as it's guaranteed that further exploration will not yield valid results. Third, by allowing the same index to be reused in the recursive call, we can include elements multiple times, enabling combinations like 2, 2, 2. In terms of data structures, the input array is sorted for efficient processing, and we maintain a result list to store all valid combinations. Additionally, we use a temporary list, current combination, to dynamically build combinations during recursion. Finally, the recursion stack handles the backtracking process, keeping track of the state as we explore different paths. Let's analyze the complexity of this algorithm. The time complexity is approximately 2 to the power of n, where n is the size of the candidates array. This is because, in the worst case, we explore all possible subsets of the array. The space complexity is n, which corresponds to the maximum depth of the recursion stack. This depth is directly proportional to the size of the input array, as each recursive call processes one candidate at a time. To illustrate how the algorithm works, let's consider an example where candidates equals 2, 3, 6, 7, and the target is 7. We'll walk through the steps to understand how combinations are formed and how the algorithm efficiently narrows down valid solutions. Starting with the example, we first sort the candidates, resulting in 2, 3, 6, 7. The recursion begins with an empty combination, a target of 7, and an index of 0. We include 2 in the combination, reducing the target to 5, and recursively call the function. We then include 2 again, reducing the target to 3, and repeat the process to include another 2, which reduces the target to 1. Since adding another 2 would exceed the target, we backtrack and explore other possibilities. Next, we include 3 in the combination, 2, 2, which achieves a target of 0. This combination, 2, 2, 3, is added to the result. We continue exploring other candidates. Including 6 results in a target of 1, which is invalid, so we backtrack. Finally, we include 7, which directly matches the target, adding 7 to the result. The final output is 2, 2, 3, 7, representing all unique combinations that sum to the target. This Python implementation solves the combination sum problem, number 39, on LeetCode. The main idea is to use backtracking to explore all potential combinations of the input list candidates that sum to the target value. #explanation. 1. Sorting the candidates. Although sorting isn't strictly necessary, it can help with optimization in some variations of the problem, e.g., early stopping. Here, it ensures a consistent order. 2. Backtracking function. The backtrack function is a recursive helper that explores all combinations. It accepts 3 parameters, remaining, the remaining sum to meet the target combination, the current combination being built, and start, the starting index for the current recursive step. 3. Base cases. If remaining is 0, the current combination is valid, so a copy is added to the result list. If remaining is negative, the recursion stops because further exploration isn't meaningful. 4. Recursive exploration. For each candidate starting at index start, the algorithm tries including that candidate by appending it to the combination list. The function recurses with the remaining sum reduced by the current candidate value. After the recursive call, the last added candidate is removed, backtracking, to explore other possibilities. 5. Output. The result list accumulates all valid combinations and is returned as the final output. #complexity. The time complexity is exponential in the worst case since it explores all potential combinations. However, backtracking helps prune unnecessary paths, e.g., when the sum exceeds the target, making it efficient for most practical inputs. The space complexity is determined by the depth of the recursion tree, which depends on the target and the smallest candidate value. This implementation is clean, efficient, and leverages recursion effectively to solve the problem. This is the Java implementation of LeetCode problem number 39, combination sum. The solution follows the same backtracking approach as the Python implementation. The combination sum method initializes the recursive process, while the backtrack method handles the exploration of all possible combinations. Key differences include the use of Java-specific collections like ArrayList and the need for explicit type declarations. The logic remains consistent with the Python equivalent, ensuring clarity and correctness. To solve this problem, we use a backtracking approach. Starting with the input candidates equals 2, 3, 6, 7, and target equals 7, we initialize an empty result list to store our combinations. The first call to the backtrack function begins with an empty combination, the full target of 7 remaining, and the starting index of 0. In the first iteration, we explore the candidate at index 0, which is 2. Adding 2 to the combination reduces the remaining target to 5, so we recursively call backtrack again with the updated combination, 2, and the same starting index. In the second iteration, we continue with the candidate 2, reducing the remaining target to 3 and updating the combination to 2, 2. Again, we recurse with these updated values to explore further possibilities. Now, in the third iteration, we still have the candidate 2 at index 0. Adding it to the combination results in 2, 2, 2, with a remaining target of 1. We make another recursive call to backtrack. However, in the fourth iteration, choosing 2 again results in a remaining value of -1. Since the remaining target has gone negative, this path is invalid, so we backtrack by removing the last 2 from the combination, returning to 2, 2. At this point, we explore the next candidate, 3, at index 1. Adding 3 to the combination gives 2, 2, 3, with a remaining target of 0. Since the target is exactly met, we add this combination to our result list and continue backtracking to explore other possibilities. Next, we consider other candidates. Returning to the initial combination of, we directly choose the candidate 7 at index 3. Adding 7 reduces the remaining target to 0, forming the valid combination, 7. We add this to the result list as well. At this point, we have explored all possible combinations for this input, and our final result for this example is 2, 2, 3, 7. With this first example complete, we move to a new input scenario with candidates equals 2, 3, 5, and target equals 8. Again, we initialize an empty result list and begin exploring combinations with backtracking. Starting with the candidate 2, we repeatedly add it to the combination until we reach 2, 2, 2, 2, which meets the target exactly. This combination is added to the result list. After exploring combinations with 2, we backtrack and begin considering the candidate 3. By combining 2 3s with 1 2, we form the combination 3, 3, 2, which also meets the target. This is added to our result list. Finally, we explore the candidate 5. Combining it with 1 3 forms the valid combination 5, 3, which is added to the result. At the end of this example, our result list contains all valid combinations 2, 2, 2, 2, 2, 3, 3, 3, 5. Now, let's look at one more example with a simpler input, candidates equals 1, and target equals 2. This demonstrates how the algorithm handles cases with a single candidate. In this final example, we initialize the result list and begin with a target of 2. Since the only candidate is 1, we repeatedly choose it until the combination becomes 1, 1, which meets the target. This combination is added to the result list. With no other candidates to explore, the final result for this example is 1, 1. This demonstrates how the algorithm can handle inputs with limited candidates, ensuring that all valid combinations are found even in simpler cases. By following this step-by-step backtracking approach, we can systematically explore all possibilities to solve the combination sum problem efficiently. The time complexity of the combination sum algorithm is primarily influenced by the backtracking process. To understand this, we analyze the maximum depth of recursion, the number of recursive calls, and the work performed at each level. The maximum depth of recursion occurs when the smallest candidate, denoted as C_min, is repeatedly chosen to reach the target. This means the depth can be approximated as target/C_min. At each level of recursion, we iterate through the candidates from the current starting index, creating a branching factor equal to n, the number of candidates. This results in a recursion tree with a total number of nodes that can be bounded by the number of combinations with repetition, given as O, n caret, target/C_min. At each node, the algorithm performs constant time operations such as appending and removing from the combination list and making the recursive call itself, which are all O(1). These components together form the foundation for analyzing the algorithm's complexity. To find the overall time complexity, we multiply the total number of nodes in the recursion tree by the work done at each node. Since the number of nodes is O, n caret, target/C_min, and the work per node is O(1), the overall time complexity becomes O, n caret, target/C_min, reflecting the exponential growth of the recursion tree as the target value increases. Now, considering space complexity, the algorithm uses auxiliary space for the recursion stack and for storing the results. The recursion stack depth is determined by the maximum depth of the recursion tree, which is target/C_min. Thus, the recursion stack space is O, target/C_min. Additionally, the result list stores all valid combinations. In the worst case, there are O, n caret, target/C_min combinations, each containing up to target/C_min elements. This gives the space required for result storage as O, n caret, target/C_min, asterisk target/C_min. Combining the recursion stack space and the result storage space, the overall space complexity is dominated by the result storage space, leading to O, n caret, target/C_min, asterisk target/C_min. When comparing this backtracking approach to a naive method, the difference in efficiency becomes evident. A naive approach would generate all possible subsets of the candidates and then filter out the ones that sum to the target. This has a time complexity of O(2 to the power of n*n for generating subsets and validating them. In contrast, backtracking avoids generating invalid subsets by pruning unnecessary branches. This improvement stems from the algorithm's ability to explore only valid combinations, significantly reducing computational overhead. Backtracking achieves efficiency by leveraging the start index to prevent duplicate combinations and by restricting exploration to valid branches. This optimization greatly reduces the total number of recursive calls compared to the brute force approach. For different scenarios, the algorithm's performance varies. In the best case, where the target can be reached with minimal recursion, such as when the largest candidate equals the target, the complexity approaches O(n). In average cases, partial combinations are frequently explored, leading to exponential complexity, O(n caret, target/C_min. The worst case occurs when all possible combinations are explored, particularly if the candidates are small relative to the target, resulting in the same exponential complexity. This exponential growth arises because each level of the recursion tree can branch into n subproblems, and the depth of the tree grows as target/C_min. Multiplying the total number of nodes, approximately n caret, target/C_min, by the constant work per node, O(1), confirms the overall time complexity of the algorithm. When solving the combination sum problem, there are several common mistakes to watch out for. First, not handling duplicates in the input can cause repeated subsets or incorrect results, especially if the array contains duplicate numbers. This often leads to inefficiency due to the exponential growth in subsets generated. A good way to fix this is by sorting the array and skipping duplicates during recursion or iteration. Another issue is ignoring edge cases, such as an empty candidates array, a target of 0, or very large values. These scenarios, if overlooked, might lead to runtime errors or incorrect outputs. You can address this by adding specific base cases to handle these situations. Finally, failing to prune the recursion tree can cause your solution to explore unnecessary branches, significantly increasing runtime. To prevent this, include a condition to stop recursion when the current sum exceeds the target. These steps help ensure your solution is both correct and efficient. Another common issue arises from incorrect base cases in recursion. If the base case is misplaced or mishandled, such as not stopping when the sum matches the target, it could prevent valid solutions from being added or even lead to infinite recursion. To avoid this, clearly define your base cases, ensuring the recursion stops when the sum equals the target or when an out-of-bounds condition is reached. Overcomplicating the backtracking approach is another pitfall. For instance, using unnecessary extra data structures or failing to properly backtrack, such as not undoing changes to the current path, can add unnecessary complexity to the code. This might lead to incorrect results and make debugging harder. To resolve this, keep the backtracking steps clean and minimal, always restoring the state at every recursive call. By keeping your recursion and backtracking well structured, your solution becomes easier to understand and maintain. When preparing for an interview, there are key insights to keep in mind for problems like combination sum. Recognizing the pattern early is crucial. Many combination or subset problems rely on backtracking as the most effective approach. If the problem has constraints, such as no duplicates or not exceeding the target, sorting the input and pruning invalid paths early can help streamline your solution. For those who find recursion challenging, iterative approaches like dynamic programming can be an alternative, though they may require a different mindset. Interviewers often appreciate when you can compare the trade-offs between iterative and recursive methods, so be prepared to discuss time and space complexity. For example, backtracking can be exponential but can be optimized with pruning. Lastly, it's important to test edge cases during the discussion. Ask about scenarios like empty inputs or other corner cases, as this shows a comprehensive approach to problem solving and prevents unnecessary surprises during implementation. Combination sum is part of a group of related problems that you might encounter, such as combination sum 2, combination sum 3, subsets, and subsets 2. Each of these problems builds on similar concepts but introduces its own unique constraints, like handling duplicates or limiting the size of the subsets. Exploring these problems can deepen your understanding of backtracking and help you identify patterns across variations. Beyond backtracking, alternative approaches can also be helpful depending on the problem's requirements. For example, dynamic programming can be used for subset sum problems, especially when the focus is on counting or checking feasibility rather than generating all subsets. However, this often requires more space due to the DP table. Iterative subset generation is another approach that avoids recursion by building subsets iteratively, though it can be more challenging to prune invalid paths. Understanding these alternatives allows you to adapt your strategy based on the specific problem and constraints. Some variants of the combination sum problem benefit from specialized techniques. For instance, sorting combined with a two-pointers approach can be highly efficient for finding pairs or triplets that meet a specific condition, though this method isn't applicable for generating all unique subsets. Another useful technique is hashing, where you can use a set to track visited subsets. This simplifies the handling of duplicates by ensuring that each subset is added only once. However, hashing increases space complexity, so it's important to consider whether the trade-off is worth it for your specific problem. By mastering these techniques and understanding when to apply them, you'll be better prepared for a wide range of combination and subset problems, both in interviews and real-world scenarios. Great job following through. Today, we unraveled the combination sum problem, explored its intricacies, and discussed efficient approaches like backtracking. Remember, mastering recursion and optimization techniques will serve you well in similar challenges. Thank you for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!